Next up, we want to figure out which molecule is polar. So first we need to, in order to determine polarity, we need to find the Lewis structure, and from there we find the molecular / electronic geometry, and then we figure out whether it's polar by examining the symmetry of the dipole moments and seeing if they all cancel out to 0 or non-zero, in which case it would be polar. So if we start with C2H4, we can already tell from its general name that it's going to be an alkene because of the CnH2n general formula. If you'd like to count the valence electrons, it's going to be 4 plus 8, so we have 12 electrons to care about. Cc, let's put a H around both of them. If we start with 1 on each, it would leave us with 2 extra electrons on the carbons, and we know carbon is optimized for 4 bonds, so let's just give it that by adding a double bond in between them. See if that adds up to our 12, 2, 4, 6, 8, 10, 12. So yes, this is our Lewis structure. And next up, we need to find the geometry by finding the hybridization of each carbon. This is going to be sp2, and this is also sp2. That's because it has 3 things attached to it. So you have 1, 2, 3. This double bond, we're going to count it as 1. And so because of that, it is going to be trigonal planar. And so it should have a shape like that on each of the carbons. And so if you actually wrote that out for each of the carbons, then you'd get something like that. And then just imagine taking it from this orientation and straightening it out like this. And instead now we get something that looks like that. Okay, and then now let's write out the dipoles to see if they cancel. So we're going to have an angle of 120 because of the fact that it's trigonal planar. This dipole is going to come this way. Okay, and so these 2 are going to cancel and these 2 are going to cancel. So due to the symmetry, the dipoles will cancel, meaning that it'll be non-polar. Let's check out our second one. We have CS2. If you want to check out our valence electrons, that would mean that we have 4 plus 6 by 2. So 12 plus 4, so 16 electrons to play with. Let's put carbon as our central because it can make the most bonds, S and S. Now if you do it this way and fill in the remaining electrons for each octet, we'd have more than 16 because we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And so the best bet would be to give carbon its 4 bonds by creating 2 double bonds. And this way we can see carbon has its octet filled, each sulfur has its octet filled. Let's check if we have 16, 2, 4, 6, 8, 10, 12, 14, 16. So our valence electrons are covered. Now let's see if the formal charges are covered too. For the sulfur, we're going to have 6 minus 4 minus 4 over 2. 6 minus 6, 0. For the carbon, we're going to have 4 minus 0 minus 8 over 2. 4 minus 4, 0, 2. So the formal charges also check out. And so now let's try and find the geometry. We have a central atom attached to 2. And so if you go to the Vesper, it has 2, and so it's just going to be linear. And so it should have an angle of 180 here. Next up, let's check in on our, so this is a correct Lewis structure, so we've just determined. Now I want to find the geometry. We found that it's linear, so we see if the dipoles will cancel again. This has a dipole pointing out like this. This has a dipole pointing out like that, which means that these 2 will cancel exactly because the 2 dipoles are equal due to the difference in electronegativity between carbon and sulfur. And so this is going to be due to the symmetry again. This means that dipoles cancel, meaning it is non-polar too. And that's your final answer for that one. Next up, we have C6H6. This one you can easily determine that it's benzene, so let's just write it out. This has 3, so it's just going to need one more. All of them are like that. And so you have 6 hydrogen, 6 carbon. You can double check on your valence electrons. We should have 4 by 6 plus 4. 24 plus 4, 28. Let's just double check that we do have that. Let's just not forget to count these as well as bonds. And so we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Sorry, let's start again. 2, 4, 6, 8, 10, 12, 14, 16. Sorry, I always forget about the hydrogens. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. And so we see all of our electrons are accounted for. And so this is going to be our Lewis structure. And then let's find out the molecular geometry. It's benzene, so it's just going to be a planar ring. And if you actually draw all of the dipoles, they should all cancel. And so this cancels this, this cancels this, this cancels this. And so due to the symmetry again, dipoles cancel. And so this is also non-polar. On to our second last one. We have SO2. Our valence electrons are going to be 6 plus 2 by 6. So that's just 3 by 6. So we have 18 electrons. We're going to put sulfur in the middle and the 2 oxygens. Start with single bonds. Fill in all of the octets. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Too many electrons. And we also know oxygen likes to make 2 bonds. So let's just give both of them their 2 bonds. We're creating a double bond here, double bond here. Okay, now let's see. 2, 4, 6, 8, 10, 12, 14, 16. And so we're going to have an extra 2 electrons left over for the sulfur. And so now let's see how many the formal charges, what they'll look like. For the oxygens, we're going to have 6 minus 4 over 2. Again, 6 minus 6, 0. For the sulfur, we're going to have 6 minus 8 over 2 minus 2. And that's going to give us 6 minus 4 minus 2, which is also 0. So the formal charges make sense and the valence electrons are all accounted for. We can also see here that the sulfur has an expanded octet. Now let's figure out the geometry. We have 3 groups attached to it, the oxygen, the second oxygen, and the lone pair. And so if we just check this out here, we have 3, but 1 is a lone pair, and so it's actually going to be bent. And so it should look like this. And so because the lone pair will repel a bit more than the electrons in these, this angle is going to be a little under 120 degrees, because this angle is going to be, of course, over 120. Sorry. Because this angle is over 120, and so is this one. It's also over 120. So this one is less than 120. And so this is what it's going to look like. Now let's see if the dipole moments will cancel. We have a dipole moment that is up towards the lone pair. Sulfur is pointing down towards the two oxygens. And so we see that indeed this can be written as this, and this can be written as this and this. So these two will cancel because the two are equal. And you're actually going to get a dipole moment. One is pointing up and the other is pointing down. But these two dipole moments will not be equal because the dipoles created by the oxygens is not equal to the dipole created by the lone pair. So because of the lack of symmetry in this case, dipoles do not cancel. And that makes it polar. So this is the only polar one that we've stumbled across. And lastly, we have CF4. Let's just double check that that is not going to be polar. We're going to have 4 by 7 plus 4, so 28 plus 4, which is going to give us 32 electrons. Carbon is going to be in the middle. Let's start with a single bond for each, and then the fluorines. Fill in your octets. And so we have 2, 4, 6, 8 on each of these, so 8 by 4, that is going to give us our 32. So our valence electrons all check out. Let's double check our formal charges. On each of the fluorines, we're going to get 7 minus 6 minus 2 over 2. That's just 7 minus 7, giving us 0. On the carbon, we are going to get 4 minus 0 minus 8 over 2, which is just 4 minus 4. Again, giving us 0. This is exactly what we expected, a net formal charge of 0. So this is our Lewis structure. Now let's figure out the geometry. And so this is going to be sp3 hybridized. And so let's just go to our chart. We see it has 4 groups and they're all identical. So it's going to be tetrahedral. And if we draw out on what that looks like, it's a bit like a tripod. Okay, and so what's actually going to happen is that you will have this dipole moment going that way. This one, since it's like a tripod, let's actually draw it on the side so that we can get a better feel for the geometry. This one is coming out, this one's coming out, and this one's coming out. And so what's going to happen is these 3 are going to cancel each other out in the x, so in the horizontal plane, and it's actually just going to leave a vertical dipole moment. And then what is going to be left is for it to cancel out with this one that is going up, and so the 2 will cancel out too, leaving no dipole moment. So with this one, due to symmetry, it'll be non-polar. And so from everything we find that the only polar one is going to be SO2. So D is going to be your correct answer.